3 minutes and 7 seconds before liftoff, the entire rhythm of the Saturn V launch operation changes. Up to this instant, the countdown has been an intricate conversation between thousands of sensors, hundreds of controllers, and the enormous 3-stage launch vehicle standing on Pad 39A. But at T-307, a moment almost invisible to the casual observer, human control steps aside. The terminal countdown sequencer takes command. This sequencer is not a modern computer. It has no microprocessor, no magnetic core memory, and no software in the sense we use the word today. Instead, it is a relay logic machine, banks of precision electromechanical relays wired to execute the last 100 or so critical operations strictly by timing, sequencing, and confirmation logic. What makes it astonishing is not its complexity, but its reliability. It must execute perfectly every single time, because in these final minutes, the Saturn V is entering a configuration so delicate, so tightly constrained, that even a pause or a few seconds of delay could cause physical damage to the vehicle or a dangerous overpressurization of its tanks. The moment the sequencer awakens is triggered by a human go from the firing room, where launch controllers issue the firing command that releases the terminal countdown sequencer, rather than a single engineer physically holding down a button. As the digital countdown clock rolls through 3 minutes and 7 seconds, the ground control system checks whether the firing command is still being held. If it is, the sequencer is released. If it is not, the Saturn V will not launch. But once that logic gate is satisfied, humans no longer have any control. You cannot pause the countdown now. The sequencer either completes its timeline, or a cutoff forces a recycle that drives the countdown back to predefined hold points, such as around T-22 minutes, with the required dwell there before resuming. With super cold cryogenic propellants already conditioning the structure from the inside, with hydraulic and pneumatic systems shifting into flight mode, and with the internal batteries beginning to assume more and more load, this is not just a procedural convenience, it is a necessity dictated by physics. The rocket must go, or it must stop entirely. Meanwhile, inside the spacecraft, nearly 400 feet above the pad, the crew is preparing for the transition from pre-launch to ascent. The command module's computer is running Program 02, the platform alignment routine that maintains the inertial platform orientation with extraordinary accuracy. The platform is floated in a bath of fluorocarbon fluid, often referred to as Freon, suspended on gimbals, with gyroscopes and accelerometers forming the heart of the guidance system. It is the only reference the launch vehicle needs once it leaves the pad. At 3 minutes 24 seconds, the astronauts prepare a manual failsafe. They key in a sequence that will allow them to tell their computer that liftoff has happened should the automatic liftoff signal from the instrument unit fail to arrive. When the Saturn V actually leaves the pad, the launch vehicle digital computer will sense the umbilical disconnect and send a signal to the spacecraft. The crew has practiced what to do if it fails, but in the history of the Saturn V, it never once failed. The crew does not press the enter key. They only arm the sequence. If the liftoff discrete never arrives, pressing enter would force the computer to switch to its ascent monitoring program. But if the discrete does arrive, as it always did, that single key press remains unused, a silent backup to a system that has been engineered to the limits of reliability.
With the terminal countdown sequencer now running, a kind of mechanical choreography begins. Pressurization valves throughout the stages begin shifting from ground vent positions to launch positions. Up until this moment, the liquid oxygen tanks in all 3 stages have been venting to maintain temperature control. These tanks contain hundreds of thousands of liters of cryogenic oxidizer, at temperatures low enough to make steel brittle and to freeze any atmospheric moisture into thick frost. As soon as the vent valves begin closing, the tanks begin building pressure, and that pressure must stabilize within tight limits, not too low, not too high, before ignition. The second stage, in particular, is tightly constrained. Its liquid oxygen tank must be pressurized within narrow limits to maintain structural rigidity and proper feed conditions while limiting boil-off. The terminal countdown sequencer checks multiple pressure sensors so quickly that the human eye cannot follow the logic on its diagnostic panels. In milliseconds, it determines whether stages 1, 2, and 3 are all reaching the required flight pressures at exactly the right pace. If any tank lags or surges, the sequencer issues a cutoff. There is simply no tolerance here. Throughout the vehicle, hydraulic systems transition from ground-supplied fluid to internal supply. In the first stage, the F1 engines rely on high-pressure hydraulic systems to gimbal the 4 outboard engine bells. Until moments before ignition, the used hydraulic fluid has been routed back to the ground through swing arm plumbing. But as the sequencer moves toward engine start, those fluid paths close. The engines now feed hydraulic fluid into their own turbopumps, preparing the gimbal actuators for the violent steering forces of ascent. Inside the command module, more transitions occur. At 1 minute before liftoff, pad communications are disconnected. The crew can still hear mission control in Houston, but not the technicians and ground personnel who have now evacuated the entire launch complex. They are alone atop the most powerful machine ever built. 50 seconds before launch, the Saturn V makes one of the most dramatic transitions of the countdown, the switch to internal electrical power. Each stage of the Saturn V carries its own set of zinc-silver oxide batteries. The first stage carries multiple zinc-silver oxide batteries for control and instrumentation. The second stage has 4. The third stage uses several batteries grouped into multiple buses, and the instrument unit carries 4 batteries of roughly 70 kilograms each. These batteries were installed less than 2 days earlier, fully charged and tested repeatedly. Now they come online. This transition is not merely a redundancy test, it is a requirement for ignition. Once the rocket begins its ascent, it can no longer rely on ground power. Thousands of amps surge through the internal buses as the rocket's electrical systems shift to flight configuration. 45 seconds before launch, the crew starts the onboard data recorder. The tape inside begins capturing sensor data and voice recordings. This is a spacecraft black box, and for good reason. During powered flight, radio communication can be interrupted by plasma sheets around the vehicle or by the geometry of its trajectory. The data recorder captures everything for later analysis. 30 to 40 seconds before launch, the commander performs the last active step by the crew before liftoff, the alignment of the backup attitude system. The inertial measuring unit is the gold standard for reference. The backup system uses coarse gyros mounted directly to the spacecraft structure. With one button press, the gyro display coupler synchronizes the backup system to the inertial platform. The spacecraft's navigation chain is now fully aligned for the violent minutes ahead. The crew has no more checklist items. Their work is done. They're strapped into couches, surrounded by switches, lights, the faint hiss of oxygen flow, and the enormous quiet of a spacecraft moments away from leaving Earth.
At T minus 30 seconds, swing arm number 1 retracts. This arm carries the final ground support electrical and pneumatic connections to the command module. When it moves away, the rocket stands entirely alone, held to the pad by 4 massive hold-down arms gripping the engine fairing structure of the first stage. 8.9 seconds before launch, the terminal countdown sequencer issues a command that begins one of the most violent mechanical processes ever engineered, the ignition of the F1 engines. These engines are each fed by turbopumps that slam petroleum-based fuel and supercold oxidizer into the combustion chamber at mixture ratios and flow rates that push the limits of structural metallurgy. The engines ignite in a staggered pattern to reduce side loads on the vehicle. The center engine lights first, then, within fractions of a second, 2 outboard engines ignite, and finally the last pair. As the first engine lights, the flame beneath the rocket is a churning cloud of carbon-rich exhaust. The Saturn V expels thousands of kilograms of gas per second, and the flame deflector channels the blast sideways into trenches designed specifically to dissipate the shock. At this moment, another event occurs that is often overlooked but critical to flight: the retraction of the cue ball cover. The cue ball is a hemispherical air data sensor mounted on the tip of the launch escape tower, containing 8 pressure ports arranged around its nose. These ports measure the angle at which the rocket slices through the atmosphere. For many hours before launch, a foam cover protects it from debris and weather. At T-minus 8.9 seconds, a steel cutter severed the copper wire holding the cover's halves together. A mechanism on the mobile launcher pulls them upward and away, exposing the sensitive ports to the air they will soon measure. At 6.4 seconds, all 5 F1 engines are running. The rocket still stands pinned to the pad. The hold-down arms monitor thrust sensors, ensuring each engine has reached the required thrust level. Only when all 5 thrust readings exceed their launch criteria does the sequencer release the hold-down arms. They pivot away in unison. For a brief instant, even with full thrust, the rocket barely moves. It must overcome 6 million pounds of weight. But as the engines reach full steady thrust, the vehicle rises only a tiny fraction of an inch at first, on the order of a few tenths of an inch, just enough to actuate release and liftoff sensing switches. This tiny movement triggers the instantaneous retraction of several swing arms that remain connected. Movies often dramatize these arms retracting one at a time. In reality, they snap back simultaneously in milliseconds, pulled clear before they can strike the vehicle.
At about 0.6 of a second after the rocket begins climbing, one of the most critical signals of the countdown occurs: the disconnect of the instrument unit umbilical. This umbilical carries data, power, and conditioning lines between the ground and the Saturn V's brain, the launch vehicle digital computer, and its guidance platform. When the connection breaks, a circuit opens, and the computer recognizes liftoff. This moment starts Timebase 1 inside the computer. Timebase 1 is the reference for every event during the first stage burn: engine gimbaling schedules, pitch and roll programs, abort mode switching, and guidance reference comparisons. Without this precise start time, the guidance equations would drift, and the vehicle could not follow its intended trajectory. The engineers who designed this system understood the danger of a false signal. Suppose wind, vibration, or an accidental mechanical strike disconnected the umbilical prematurely. The computer would then incorrectly assume liftoff. To prevent this, the launch vehicle digital computer cross-checks the accelerometers. Only if it sees at least 1 gravity of upward acceleration after guidance reference release does it accept umbilical disconnect as genuine. This layered logic means that only true physical ascent can trigger Timebase 1. But on every flight, including Apollo 11, the sequence was perfect. The Saturn V was climbing, the umbilical disconnected, and the launch vehicle digital computer began its ascent program without ambiguity. Within the first second of powered flight, the computer transmits the liftoff discrete to the command module's computer. Inside the spacecraft, several indicators respond instantly. The liftoff light illuminates, the mission timer starts from 0, and the commander calls the words that have echoed across every crewed American launch since Mercury: "The clock is running." At this moment, all human involvement in the launch is effectively complete. The Saturn V is in the hands of its guidance platform and digital computer. It is a fully autonomous, 6.5 million pound spacecraft rising on a column of fire visible for dozens of miles. The next stages of flight, the pitch program, the roll program, the reduction of loads as the vehicle breaks the sound barrier, the shutdown of engines, staging, and the ignition of the second stage all flow from this one moment. The last 3 minutes before Saturn V liftoff are no longer a countdown. They have become the opening chapter of a mission to the moon. If you enjoyed this dive into the final moments before Saturn V liftoff, a like or a share really helps more people discover these stories. And if you want to support the channel and get early access or members-only videos, you can join the channel anytime. Thanks for watching and for keeping Apollo history alive.